Hello class, this is Mr. Kreitz's physics class, not related to Mr. Sherman's class because this one's better. That's not true.
Ha.
So what we're learning today, we're learning force equals m times a. This is like the Goldilocks of equations. This is the best equation you will ever know or ever need to know. So much, in fact, we learned it first semester, we still need to know it in second semester. It's that important. It's Newton's second law, and that's kind of just an equation form. But, I'm not going to give you the long form. That's boring. Sorry, Newton. I didn't mean that. So here we go. Force equals force. M is mass. A equals acceleration. That's a really big word. Bam and bam. All right, here we go. Force is measured in newtons. Newton force. M, well, we're going metric here, so grams, kilograms, milligrams, hectograms, never mind. Acceleration, it is in meters per second. Now, there is one catch, though, about acceleration. If it is a constant velocity, or it's not moving, acceleration is 0 meters per second. Why, you may ask? Well, because if an object is going 50 miles an hour, and it's still going 50 miles an hour, is it going any faster or slower than it was before? The same speed. So therefore, that is a catch, which would then negate the mass and cancel it all out. But I digress. Now we're going to learn here, we're going to learn about forces more in depth. Woohoo! We're going to learn about pushing or pulling of forces and what types of forces there are. For example, we have we got some contact forces. When you come in contact with something that causes you to move or a force to be acted upon you. So let's say Robbie's fist comes in direct contact with you and applies a force. And then we're going to do some wind action. The wind is pushing, the air molecules are hitting you, and they're directly hitting your body, and they're directly pushing you. Now, one last one. Friction, everybody's friend. We would not exist today if it weren't for friction. For that, it deserves 3 underlines. Friction is a direct force because I'm able to walk right now, because you can't see my feet. I'll show you my feet. I'm able to walk now because of friction. Because of the static friction, I can push off the ground. If I couldn't push, I would just slip. So friction is very important. Now we're going to switch over from long range to long distance. Bam. Woo! Nick! Long distance forces are forces that come from long away and affect you. That would make it seem like the wind would be a long distance force. It is not. Long distance, long range, kind of talking about like gravity stuff. So, gravity. Is gravity the feeling of gravity? Like so. It pulls the ball down. If it weren't for gravity, and it's kind of long range in the sense that the gravity of the Earth is what's pulling it down. And the Earth's core is where the gravity emanates, because that's the densest part of the Earth. And so it's being pulled all the way from the Earth's core to the Earth's core, but it can't make it there because there's a floor in the way. I could do this for days. Magnetism. Oh, don't not get me started on magnetism. Isn't that right, Rob? Magnetism is also a long-range force because I can have whoa. Oh no, I broke it. I break things, but we won't talk about that. And because why not? The force. Not to be confused with Newton force, but the force, like metachlorians, which Corians? Maybe? Which that was a terrible movie. I don't know why they put that in there. I hope Disney does a better job. That was unbelievable. Just a quick recap so you guys don't forget. Here's what force looks like. And mass. Show them what mass looks like, Nick.
Okay.
Show the class what mass looks like.
I can't live that. No, never mind.
And what's the last part of F equals M?
A.
A. What does A look like?
Dude. Okay. Okay, I'm talking about free body diagrams. This looks a little bit sloppy, but it's what it says. Okay, free body diagrams, really simple. Take that tennis ball as an example. It's a tennis ball. Oh, yes, Zach. Okay. Unlike that, free body diagrams are pretty simple, nothing fancy. So, one free body diagram would be like this. And since the ball is just sitting there, it's like, only has two forces acting upon it. That would be normal force and the mass, the weight of it. Mass times gravity. And gravity equals 10, as we all know, because that's just kind of obvious, or at least on Earth. And since force equals ma, that's the sum of the forces, so it'd be N minus mg because they are opposite forces. So N minus mg equals ma. And since this ball is not moving, obviously, is it moving, Robbie?
I don't think so.
Yeah, it's definitely not. Okay, so since the ball is not moving, the ball is not moving, so the acceleration would equal 0, and 0 times any number on this side would be 0. So that's a 0 right there, obviously. So it'd be n, let me just erase that really quick. N minus mg equals 0. So you could just like add mg to both sides, so it'd be n equals mg. Yes, that's exactly what it is. And that's it.
This is Veritech.